Okay, so we want to prove this theorem now. So what we need to prove, the difficult part of what we need to prove is that if gy is equal to hx, then there's some function little f such that big F is equal to the gradient of little f. Okay, and so what we're going to do is we're going to construct a function and verify that it satisfies the properties that we need it to have. Okay, so here's how we want to think about it. We're going to define a function f of xy. This is going to be equal to the integral from t is equal to 0. It doesn't have to be 0. It could literally be any number. T is equal to 0 to t is equal to x of the function g of ty dt plus some unknown function of y. Okay, and we're going to have to figure out, we're going to go through and figure out what function or what phi has to be. But the first thing that I want you to realize is that by the fundamental theorem of calculus, the partial derivative of f with respect to x is going to be equal to g of xy plus the partial derivative of phi with respect to x. But phi is just a function of y, so this is equal to 0. We need to show that the derivative with respect to y is equal to h. Okay, and we're going to have to make that happen, we're going to have to define phi in a certain way. Okay, so the partial derivative of f with respect to y, well, this is going to be the derivative or the integral from t equals 0 to x, the partial derivative of g with respect to y, g of ty, plus the derivative, it's just the regular derivative of phi with respect to y, because phi is only a function of y. Okay, and now here's where we're going to use our assumption. The derivative of g in the y variable is equal to the derivative of h in the x variable, or in this case, the derivative of h in the t variable. So what this tells us is that this right here, this is equal to the partial derivative of h with respect to t of tx, or ty, plus phi prime of y. Okay, but now we are integrating with respect to t, and we're taking the derivative with respect to t. So this is equal to h, by the other part of the fundamental theorem of calculus, this is equal to h of xy minus h of 0y plus phi prime of y. Okay, this is the partial derivative of f with respect to y. Now, if we want f to be a potential, if we want the gradient of f to equal to g comma h, we also know that the partial derivative of f with respect to y is equal to h of xy. Okay, so if that's true, then this is also equal to h of xy. And so what this tells us is that phi prime of y is equal to h of 0y. This tells us that phi of y is equal to the antiderivative pretty much of h. So phi of y is going to be equal to the integral from t equals 0, or let me use a different letter. Now I'm just going to use t. T equals 0 to y, h of 0y, h of 0t dt. Okay, that is what phi of y is. So overall, f of xy is equal to the integral t equals 0 to x of g of tx, ty dt plus the integral t equals 0 or any other number to y, h of 0t dt. And the 0 here doesn't need to be a 0, but it just has to be whatever that is equal to there. Okay, now this was kind of a complicated derivation. When we actually do this, it might go a little smoother and might make a little more sense. But this is what we have here.